Hello and welcome. In this video, we are going to take a look at second-order differential equations. So we tend to live in a second-order world, and so it's not uncommon to see second derivatives in real-world phenomena. So most commonly, you might have seen second derivatives in applications involving acceleration of some sort of body over time, whether that be a car or a bike or some sort of object floating through space. So before we get started in this, let's motivate the development of a model with just a little bit of algebra first. So let's say that we were faced with this second-order homogeneous constant coefficient linear differential equation. The second derivative minus y equals 0. Now let's for a second observe that the reason this is called second order is because the highest derivative present is the second derivative. Constant coefficient is something that is convenient for a differential equation. Notice that the coefficients of all the terms involving y are constants. Here we could place a 1, here we could place a -1. And so that explains the constant coefficients. Linear because we have y to the first power, so therefore our classification system works again. So if we look at this equation and we wonder, well, how do we go about solving this? You can't really use separation of variables in the same way that we were able to with first order. But if we begin to think about what this equation is saying, it lends us insight into what the solution might look like. So here we're saying, and I'm going to go ahead and use the y prime prime notation here. And the reason I'm going to do that is just to save on having to write the second derivative. So if I add y to the other side, I see that what I have to satisfy in order to solve this differential equation is that the second derivative of y has to equal y. So the second derivative of y must equal y. Well, we begin thinking a little bit about what functions we know whose second derivative equals the original function that we started taking a derivative of. Well, I can kind of begin exploring this to see if I can guess any functions that would work here. And I can say, well, geez, let me think of some candidates. And I like to use the word candidates because these are not necessarily solutions, but these are just my guesses. So you can think about these as educated guesses. Now, I'm going to be really sort of out there right now, and I'm going to say, well, what about something like e to the t plus t squared? Well, I have to make sure that in order for it to solve this equation, I have to make sure that the second derivative of what I pick as my candidate is the same as the original function. Well, I take the derivative of this, and I see that it's going to be e to the t plus 2t. And now if I take the derivative of the derivative, I get e to the t plus 2. And we notice the relationship between y and the second derivative, these two functions, we see that they are not equal to one another. And therefore, since they're not equal to one another, then this means that this is not a valid candidate solution. So I have to begin thinking, if I'm going to be strategic here, not just guess, I have to guess things that I know that when I take their derivatives, eventually I get the same function back. Well, another guess might be an exponential, because here I even see that an exponential, when you take its derivative, you keep getting the same function back, right? So if I take the first derivative and I see that, I take e to the t, and now y prime equals e to the t, and y double prime equals e to the t, I see that that does, in fact, work here. So the reason I see that that works is because these two are equal, and I want to make sure that they're equal before I claim that they are, in fact, solutions. So, our solution here is that y equals e to the t is a solution. Now, you may not see this at first, but you can keep playing around with this. Unfortunately, things like y equals e to the 2t won't work, anything where the exponent is not related to 1, because when we take derivatives of e to the 2t, we have to use the chain rule on the exponent and multiply it by the derivative of the exponent. And so by the time we take the second derivative, we get 4e to the 2t, and clearly these two are not equal. Now, one other solution that would work is y equals e to the negative t. And the reason that will work is because when I take its first derivative, I get negative e to the negative t, or negative 1 e to the negative t. And if I take the derivative of that, now I'll get negative 1 times negative 1, which is positive 1. And we see that these two are, in fact, equal. So here, we do have equality. And so y equals e to the negative t is also a solution. Now, to keep these distinct, because I want to refer to these as different solutions, so perhaps I'll call this one y1, and this will be y1, y1 prime, y1 double prime, and we'll call this y2, and the y2 prime, y2 double prime. That way I see I have two solutions. Now, one interesting thing that we'll notice is that with second order differential equations, we will have two solutions. And this is a very common feature. Let's take a look at another example before we delve any deeper into some of the building blocks here. So here we notice that it's almost the same equation, but we have to ensure that the second derivative is equal to 4 times the original function. Now clearly e to the t won't work because its second derivative is exactly the same as the function we started with. E to the negative t won't work as well because it is exactly the same as what we started with. What I have to ensure is that y double prime is 4 times bigger than y itself. And if I look at one of my guesses here, or one of the things I was playing around with, if I chose y equals e to the 2t, then its second derivative, we've already calculated, is 4e to the 2t. And check this out. If I now substitute these in to see if they're equal, and by the way, checking second order solutions is exactly the same process, is that equal to, question mark, 4 times y, which is e to the 2t? Well, 4e to the 2t is in fact equal to 4e to the 2t, and therefore y1 equals e to the 2t is a solution. In fact, you could put any coefficient in front of e to the 2t. For example, if you put 7 here, then this number here would just be 7 times 4, which is 28, and still that would be 4 times bigger than the original equation. So any constant out front will work, but the exponent of 2 is necessary because that's the only way I could develop new coefficients. The original 7 here just follows along all the way down, and it never changes only by virtue of the fact that it gets multiplied when we take derivatives. So the next question is, would there be any other solutions? Well, naturally, if I want the second derivative to be 4 times bigger, I can also look at e to the negative 2t, because when I take derivatives, again, it requires 2 derivatives to get something to be 4 times as bigger as the original function. The first derivative pulls the 2 down once, the second derivative pulls the 2 down again. So let's see if this one works. Y prime equals negative 2e to the negative 2t, and y double prime equals negative 2 times negative 2, which is 4e to the negative 2t. And to just check my work, I have to see, does the second derivative of y equal 4 times y? And well, if I substitute in what y double prime is, it is 4e to the negative 2t, and does that equal 4 times e to the negative 2t? And you can see that clearly these are going to be equal on both sides. So this solution here, which I'll just call y2, gives me a second solution. And once again, you see that up here, I kind of mentioned that, well, second order differential equations are each going to have two solutions. And we'll see shortly why that is. But for now, it's purely speculative. E to the negative 2t is a solution. Okay, well, right now, the fact that we have two solutions may raise a question in our mind as to, well, what do we do with the two solutions? Which one do we use? How do we use them? Do we use them both? Do we combine them in some way? And in short, the answer is yes, they do get combined, and you use all the solutions to form a general solution. Okay, so what can be said generally about this type of differential equation? So notice that what we changed, one of the things in mathematics is that we often want to observe patterns. And the only difference between this equation and this equation down here is they're both subtracting the second derivative in the original function. The only difference was the coefficient in front. Well, I'm going to make the argument that I'm seeing a pattern here, that if this had been y prime minus, 9y equals 0, then I would be willing to bet that e to the 3t and y2 equals e to the negative 3t would be solutions. Because in this case, this is suggesting that the second derivative has to be 9 times bigger than the original function itself. Well, if I take the second derivative, remember the first derivative puts that first instance of the 3 down as a coefficient, and then the second time you differentiate it, it becomes 3 times 3 e to the 3t. So the square of this number right here has to equal the coefficient that we want in front of the 9. And same thing will happen here. y2 double prime will be negative 3 times negative 3 e to the negative 3t. So I'm going to hypothesize, hypothesis is that if I had y double prime minus some constant, we'll just call this, what do we want to call this? We'll just call this minus a times y equals 0. We would be willing to guess that y1 equals, well, what was the relationship between the 9 and the 3? The relationship between the 9 and the 3 was that we would expect the exponent to be the square root of that number, like so. And y2 would equal e to the negative square root of a times t. Now, t is not in that square root, so important detail there to note, because these can often start to look the same, but you have to be really cautious. And let's just make a quick proof here. Well, if in fact these are solutions, that means y1 equals e to the square root of a times t. Its first derivative would bring that first instance of the square root of a down. So square root of a, e to the square root of a t. And then the second derivative would bring the square root of a down again, and you'd have square root of a times square root of a, e to the square root of a times t. Now that's going to give us square root of a times square root of a is just a, e to the square root of a times t. That is all great. Now we just have to check that it actually satisfies the equation up here. So does y double prime, or I should say y1 double prime, minus a times y1 equals 0? Now we could have also said, does y double prime equal ay? That would have been fine as well, but putting it into the original equation, I see that y1 double prime is a e to the square root of at minus a times y1, which is e to the square root of a times t. And I can see that those are exactly the same, and therefore they will cancel out and give us 0. And a similar argument can be made for the negative square root. The intermediate first derivative, by the way, is not a derivative that we actually use. Right? That first derivative is just a stepping stone to get us to the second derivative. The first derivative has not come into play yet in these second order models. So we've proven for y1, similar proof would hold for y2. So we've just solved a whole kind of family of differential equations without having to do very much calculus, just a little bit of differential calculus. Now let's modify this equation just a bit. Here we're saying that the second derivative plus y equals 0. Now wait a minute, what's the difference between this and what we had over here? Oh, there's a minus sign. Here there's a plus sign. Do the same guesses work as in question 2? Well, let's see. If we had said y equals e to the t, we already know that y1 double prime is equal to e to the t. And if we were to check whether that's a solution, we would have to say, does the second derivative plus the original function equal 0? And, well, the second derivative is e to the t. The original function is e to the t. Do those two things add up to 0? And the answer is not really, because 2e to the t is not always equal to 0. In fact, it's never equal to 0. So these will not work. Same thing for y1 equals e to the negative t. Its second derivative will be the same, and when you add them, you just get something that's twice as large instead of something that cancels out. So that plus sign here makes all the difference for e to the t. Now, what other candidates do we think of? We already said that the function and its second derivative must somehow be related. That is, we notice that the function and its second derivative have to sum to 0. Well, that tells us that those two functions must be similar in some sense. So what other functions do we know that we can take derivatives of and still somehow retain the original function? For example, you can probably agree that if you had t squared, that wouldn't work because its second derivative is going to be 2, and 2 plus t squared is not equal to 0. So that wouldn't work. Well, how about sine and cosine? Well, if I picked y equals sine of t, now another key here is that if you rearrange this equation, it says the second derivative has to be equal to the negative of y. Now all that means it just has to have the opposite sign as y does. So it doesn't mean y has to be negative, it just means y double prime is the opposite of y. So we take a look at this one here, we see that the derivative of sine is cosine, and the derivative of cosine is negative sine of t. And we see that the relationship between these two is such that y prime is the opposite of y. So does the second derivative plus y equals 0? That's what our check is going to involve. The second derivative is negative sine t. The first function, or the original function, is sine of t. And clearly, negative sine of t plus sine of t add to 0, and 0 equals 0 is a true statement. If it works for sine, I wonder if it works for cosine. So let's also try, because we said there's going to be two solutions here. So let's also try, as a second guess, y2 equals cosine of t. Well, its first derivative is going to be sine, rather negative sine of t. And the derivative of the derivative is going to be negative cosine of t. And so once again, you see that if you add these two functions together, they are going to cancel out and give us 0. So does y2 prime plus y equals 0? Question mark. We plug them in. We have negative cosine t plus cosine t. Does that equal 0? Of course, because 0 equals 0. So we have two solutions. We have the first one being y1 equals sine of t, y2 equals cosine t. Not specifically in that order. Whether you found cosine or sine first, it doesn't make a difference. The subscript is strictly there to help us keep track of the fact that there's more than one solution. Now we're starting to get into those ones where the coefficient here changes. And if that coefficient changes, we have to adapt our guess, right? Because if you look at this relationship, this says that second derivative has to equal the opposite of 4 times y. So it worked up here because the second derivative had to just simply be the opposite sign of y, but now it has to be the negative 4 times bigger. So if one of the common things that people want to try is they want to say, well, what if I just put something out front, like y equals 2 sine of t? Well, unfortunately, that's not going to work, because when you differentiate something that just has a scalar in front of it, or a constant, I should say, it stays there all the way down. So its second derivative is going to be the opposite sign, but it's not going to be, whoops. It is not going to be 4 times as large. So you can see that they're opposite signs, which the 2 would have worked up here, since 2 sine of t minus 2 sine of t is 0. So one thing to note is that any constant multiple of a solution is going to work, but this 2 here is not going to allow the second derivative to be 4 times bigger. So we got to kind of think about chain rule here. If instead what I did was put that 2, let me try this, sine of 2t, and the reason I'm doing this is because I know with the chain rule, every time I take a derivative, that 2 is going to pop out. So the first derivative will be 2 cosine of 2t, and the derivative of 2 cosine 2t will be 2 times 2, rather negative 2 times 2, because the derivative of cosine is sine, and that will be sine of 2t, which is equal to negative 4 sine 2t. And now if you check, does the second derivative of y1 question mark equal negative 4 times y1 itself? Well, let's see, y1 double prime is negative 4 sine of 2t. Does that equal negative 4 times y1, which is simply sine of 2t? And clearly these are equal because negative 4 sine 2t does in fact equal negative 4 sine 2t. So we've done good. We now know that y1 is, and you can see the relationship here. If this were a 9, this would have to be a 3. If this were an 8, this would be the square root of 8. This number here has to be the square root of this coefficient because it takes 2 derivatives, or 2 multipliers of 2, to build up to that 4. And another one that will probably work is y2 equals cosine 2t. For similar reasons as above here, its first derivative will be negative 2 sine of 2t. You take its derivative again, you get another multiple of 2, which is going to be negative 4 cosine of 2t. And you can see that y2 prime is in fact negative 4 times y2. So there's one solution, there's another solution, and you can see that again, we have 2 solutions to a second order equation. One of the intuitive questions we might have at this point is, well, when does this apply? When are we going to need this? So we're going to take a look at the example of a spring mass system. Spring mass systems are often described in physics as you have some sort of wall or stationary point, and you have some mass attached to it. So it could be a weight of some sort, and between that weight and that that fixed stationary wall or ceiling, there's a spring. And if we all know that if you were to pull this side out to the right here and release it, that spring would want to bounce back and forth until it sort of slows down, fights the forces of friction, and comes to a rest. The other examples are buildings and earthquakes. So if you think about a building and you think about what happens when that building it encounters an earthquake down here, this thing is going to kind of sway from side to side a little bit, right? It's going to kind of do this and sway over here. It's going to sway back and forth to try to stabilize itself out. Also, whenever you think about a strut or shock assembly, shock and strut assembly in your vehicle, you know, your vehicle, and this is going to be a very, very poor rendition of a car, but in your wheel well, right, you have your tire attached down here, and your car is, of course, resting on that, and every time you go over a speed bump or something, you can feel that you have something in there that's sort of breaking that fall, so it doesn't feel like you hit a big lump. So anything that has suspension, also electrical circuits, behave like spring mass systems, although we won't go into that here. So this basic model, even though it seems like contrived physics problem is really important in describing a lot of types of motion. So here we're going to have a mass. This is going to be m, and it's often measured in kilograms. Okay, it doesn't have to be measured in kilograms, but we like to stick with metric units. B is, well, let's look at K first. K is what we call the spring constant. And every spring has a spring constant. And we'll describe what the spring constant actually does in a moment here, but it kind of describes how stiff or how stiff the spring is. So a stiffer spring, like one in the car, is going to be valued at a higher K than, say, like the spring in your mechanical pencil. That's going to be a very low value of K. Now this thing is going to be measured in newtons per meter. So basically it's the amount of force that is applied for every meter of displacement, and that is assumed to be constant. And so then we also have this thing called B, and you might be wondering what this is. Well, oftentimes this is referred to as a dash pot, and this is what we call the damping coefficient. So in the spring, there's actually something called a strut that kind of comes down through here, and it uses pneumatic pressure so that even though the spring will continue oscillating, but this, what it does is it resists the oscillation and it kind of slows them down. So, for example, if you've ever seen a door in like a mall or a store, that door never slams shut. In fact, if you look at the top of the door, there's usually some sort of hinge that has some tube-like structure. This thing here is often referred to as a dash pot. So as this thing moves back and forth, the two ends of this little guy kind of create friction and slow this down. It's kind of a weird illustration, but anything that's going to slow down the oscillations. And this is going to be measured in newtons per meter per second. So basically this is the amount of force that this damping coefficient applies for every unit of velocity. Something you'd get into more in a physics context. Okay, so furthermore, suppose there's something that dampens the oscillation of the back and forth movement. We will call that a damper. So if we stretch the mass, for example, we expect the release of such a mass to result in slowly diminishing movement until finally the mass comes to rest. So we should kind of expect this to slowly stop oscillating because there's enough friction here that is sort of overtaking the force of that spring. So let's build this model. This model starts off with Newton's second law, which basically says the net force is equal to mass times acceleration. So all forces are additive, meaning we sum the forces to get the net force. Okay, so what kinds of forces do we have in here? Well, we have the force of the spring, and there's something known as Hooke's law that describes how this happens. This is taken from physics, and as mathematicians we probably don't need to worry too much about it. We just need to know that this is something that physicists have studied. So the force sub spring, that's just allows us to see that that's just due to the spring itself, is negatively proportional to the displacement. Now this should make sense if you've ever stretched a spring, and let's just say here you have your spring, and here is its rest point. Here's where it would want to be if you didn't do anything to it. So if you just let it sit, it would sit in its normal position. Now imagine that you stretch this thing out, and you continue stretching it out this way. Where does that spring want to go? Well, the spring wants to go back to rest, right? So the force is this direction, and the more you stretch it out, the stronger that force is in that direction, which explains why the spring force is negatively proportional to the displacement. So if we define y equals 0, y is the displacement from rest. From rest point. So if you put no compression or stretch on that spring itself, it would want to stay coiled up right here and stay stable at y equals 0. Now we're going to define any movement going this way to be y greater than 0. That's going to be a stretch. And we're going to define y less than 0. So if you go this way, we're going to define that to be a compression. Now, so if you compress the spring, it wants to go the opposite direction. And the more you compress it, the stronger that force is in the opposite direction, which is really all Hooke's law is saying. Now, all forces that resist movement of the spring are bucketed into the damping force. So we'll say the damping force, what it does is it opposes velocity. So for example, if that spring is moving this way, the damping force will proportionally slow it down, right? So it's still going to allow that spring to move this way, but it's going to start to slow it down until it goes back, and it's going to slow it down, and it's going to slow it down until eventually that spring kind of stops moving and it stays fairly stationary. The final force that we'll consider is that of what we call forcing functions. Now, forcing functions are forces that are not inherently part of the spring mass system. For instance, the force of gravity, that has nothing to do with the spring mass system itself. That is an external force. And from physics, what we know is that the force of gravity is the mass multiplied by the gravitational constant. I think it's negative 9.8 if you're dealing with the metric system, and that's just going to be written as m times g. So the forcing force, we just call that F sub force, is equal to mg. Now, according to Newton's second law, if we want to sum all these forces, so force equals, there's the spring force, there's the damping force, there's the gravitational force, that's what replaces F, and that's equal to mass times acceleration. Now, where does the second derivative come in? Well, acceleration, A, that's the second derivative of displacement from rest with respect to time. Therefore, we could replace A with the second derivative. And that leaves us with the sum of the three forces equals mass times acceleration, which after rearranging, typically we want all the functions of y on the left and everything else on the right. So if you add b dy dt to m times acceleration, if you add ky to that, then you get something that looks like this. Now, the mass value is in front of the acceleration terms, but if we divide both sides by it, then the damping force gets divided by m, the spring constant gets divided by m, and I guess technically so does this over here. Now, with that said, this forms what we call a non-homogeneous second-order linear differential equation. So it's non-homogeneous if the left-hand side, if the right-hand side. So if this right-hand side was 0, as you see, all the y terms have been, anything involving y has been moved to the left. If what you have on the right is not 0, then it's non-homogeneous, just like with first-order equations. If this does end up being 0, for example, let's say you're ignoring the effects of gravity, or gravity is not really coming into play because of the way the spring mass system is positioned, then this could end up being 0. There's no external forces beyond that of the system itself. If you remove this mg, it would become a homogeneous. So if this were 0, or if you were in a gravity-free zone or a vacuum of some sort. Now, if you kind of look at this thing and you write the second derivative as y double prime, you can see that these are constant coefficients right now. The damping force, the mass, and the spring constant are all fixed in that situation. They're not functions of time. But in general, if we go beyond just the spring mass system, we may want to study situations in which this coefficient is not a constant, but it's some function of time. So we're just sort of broadcasting forward, we're foreshadowing what's to come later. Same thing here. This in general doesn't have to be a constant. It could be some function of time. And that this over here can also be some function of time. And so this would embody the non-homogeneous second-order linear differential equation that we want to study. So let's go ahead and take a look at the simple case. Suppose we let b equal 0. That is, suppose there is no damping force. This absence of damping force means there is an overall absence of friction of any sort. Now we're going to, going forward for a little while, we're going to assume there's no forcing function. We're going to focus on the homogeneous case. And if we let b equal 0 and we let k equal 1 and m equal 1, you can see that here we'll have the second derivative plus 0 over 1 times y prime, so that term goes away, plus 1 over 1 times y equals 0. So that's why this coefficient is a 1 here. This is the k over the m, the 1 over the 1, which is 1. Now we've already solved this equation. We already know that there are two solutions that will work. y1 equals sine of t, and y2 equals cosine t. Perfect. So now we have two separate solutions, but we really need to know what to do with them. In order to understand what to do with them, we use what's called the superposition theorem. The superposition is kind of like when you superimpose an image over another one. It makes it look like you can put somebody in a different background. Excuse me. So if I take a picture of myself and I put it, kind of Photoshop me into a situation where I'm in Disneyland, but I'm not really there, that's called superimposing, but superposition is very similar to that in concept. So given a homogeneous differential equation, which includes but is not limited to the spring mass system, if two linearly independent solutions can be found, right now don't worry about what that means, linearly independent means that they're not just multiples of one another. So cosine and sine are two entirely different functions. So if you can find two solutions, y1 and y2, then any linear combination is also a solution. Y of t equals some multiple of y1 plus some multiple of y2. These guys here are, we have two arbitrary constants. And just to provide insight into this, according to our solution, our general solution would be k1 sine of t plus k2 cosine t. And how do we know that that's a solution to this equation? Well, we'd have to compute its second derivative, which would be, let's see, k1 sine of t, its derivative would be k1 cosine t. And remember, k1 and k2 are just constants. Minus k2 sine of t. And if we take the derivative of that, k1 cosine of t, its derivative is negative k1 sine of t. And the derivative of k2 sine t is minus k2 cosine t. And if you add these together, what should they give us? Well, if we add the second derivative to y, they should cancel out and give us 0. And these two added together, negative k1 sine t plus k1 sine t. Negative k2 cosine t plus k2 cosine t, they cancel out and give us 0. So y double prime plus y does in fact equal 0. So that's how we know that's a solution. So superposition really just puts two solutions, smashes them together. And the reason this really works is just because you're adding. When you're adding and you're dealing with derivatives, the derivative is a linear operator. So it takes the derivative of each term in the same way. Given no damping, what is the general solution? So our general solution, we just said, was any multiple of sine t plus any multiple of cosine t. Now, the reason we have two arbitrary constants is because we have one, this is our initial position, and also, so if you pressed play on the image, you would not only see that spring mass system stuck at a certain point, but the second you press play, it would start to move. And therefore, it's going to also have to have an initial velocity. So let's think about what's going on here in this picture. So we have some spring mass system, and it doesn't matter where we draw it. Now I'll draw it vertically this time. So here I have some mass attached to it. Now it's not at rest. Its initial position at time 0 is 1 unit of stretch. Remember, we said that positive will mean that it is stretched. So this distance from here to here is 1. And because we are in the metric system, that's going to be 1 meter. Also, y prime of 0 equals 2. It's a positive number, which means it is going to continue stretching. So when we press play, that spring mass system is going to continue moving downwards. So how do we actually work with these two initial conditions? Well, the first one is a value of the position, and this is my position function. This initial velocity is a value of the velocity function, which is the first derivative of position. So in order to solve for the constants, I actually have to find the velocity function, which we said was k1 cosine t minus k2 sine t. And this is our velocity. Right? So once we have the solution for position, we can take derivatives all day long. And now we're going to make the substitution. Here we said the initial position for the position function. The initial position function will have a value of y when t is 0. And equation 2, the velocity, will be positive 2, k1 cosine of 0 minus k2 sine of 0. Okay, so we have a system of equations to solve. The good news here is that sine of 0 is 0, so that will be 0. This will be 0. And cosine of 0 is 1, and cosine of 0 is 1 there as well. So the two equations that we actually get are 1 equals k2, and the second one says 2 equals k1. So our final solution for our particular solution for this model is going to be y equals 2 sine t plus 1 cosine t. And let's just go ahead and take a look at this in Desmos to see what's going on. So here we have the solution, 2 sine x plus cosine x. And remember, one thing that we want to note here is the x-axis is time, and this is going to be measured in seconds. The y-axis is position from rest, measured in meters. And so one thing that we want to just verify in this solution is what's the initial condition? Well, initially the mass or the spring is stretched by 1 unit. Y equals 0 represents the equilibrium or the rest position of the spring. We also see that the spring is, now we can't actually compute, we can check that the second derivative, or that the initial velocity is 2, but definitely we describe that the spring mass system is stretching. Now I'm going to do something cool here. I'm going to insert a slider for time, and I'm going to set time to go from 0 to 12 seconds. So what I'm going to do here is I am actually going to plot a point, and I'm going to plot the point 0, and let me call this function here f of x equals. So what I'll plot is 0, f of t. Now all that's doing is that's going to show me a point on the vertical axis, so that the t value is not going to change, but the y value is going to be the current value of where that spring is. So what this is going to do, and I'm going to slow this down a bit and have it just do it one time. So watch what happens. So if you watch this green dot, that's just describing, that's basically the spring mass system oscillating up and down. So now it's going to, at first it goes to a stretch, it goes into a stretch, rest, compression, rest, stretch, rest, compression, rest, and so on. Now one thing that we should notice is that we would ideally like the spring mass system to come to a stop, but we've assumed no damping. That is, we have no friction, we have no gravitational pull, and that's why this is what's happening. Now, another thing I could have done is I could have just plotted the point t f of t. So watch this. Now we'll have both the green and the purple dot moving. The purple dot is actually following the curve, but the green dot is just keeping track of the vertical position of that purple point. So that becomes a very handy tool to have. So let's suppose that we just adjusted our system a little bit, and we said that let k equal 8. Now from our spring mass system, the second derivative plus b over m times the first derivative plus k over m times y equals 0. And we've just said b equals 0, so this whole term will go away, because 0 over 1 will be 0. And so we'll be left with the second derivative plus 8 over 1, which will just be 8y equals 0. Now we've already kind of described how the solution changes the input, and we can verify this for sine is going to be the sine of the square root of 8t. And the reason that's going to work is because when you take its second derivative, the square root of 8, two multiples of that will come out, and you'll have 8, negative 8 sine of the square root of 8t. And if you take the second derivative, negative 8 sine square root 8t, plus 8 times positive sine square root 8t, they cancel out and give us 0. Also, y2 equals cosine of square root of 8t. That's also going to work. And for the same reason, now our general solution is going to be any multiple of the first, which is sine square root of 8t, plus any multiple of the second, cosine of square root of 8t. Now for our initial conditions, we're going to need the velocity function. So the first derivative of this solution is going to be square root of 8 k1 cosine of the square root of 8t. And that's going to be because of the chain rule. And then I'll have the derivative of k2 cosine square root of 8t will be negative square root of 8 k2 sine of square root of 8t. And now again, I'll plug in my initial condition. For my position, it is 1 equals, now the first term is going to be k1 sine of 0, which is just 0, plus k2 cosine of 0, which is just 1. For the second equation, y prime, so that's going to, y prime is 2 at times 0. Square root of 8 k1 cosine of 0 is 1, so square root of 8 k1 times 1, which is just square root of 8 k1, minus, this is going to be 0 because sine of 0 is 0, and so this leads to giving me a k1 of 2 over the square root of 8. So my general solution, or my particular solution for this set of initial conditions is going to be y equals, we said 2 over the square root of 8. And you can leave it like that. No need to reduce this down or rationalize denominators. We'll leave it like that. And then plus our k2, which is 1 cosine of the square root of 8t. So let's go ahead and compare our solutions. And so now we have 2 divided by the square root of 8 times the sine of square root 8x plus 1 cosine of square root 8x. And just double checking that. That's what we should have. And one of the things you notice right away is, first of all, the initial conditions are both the same for the only thing that's changed here is the spring constant. Here we made the spring kind of stiffer, and one thing that we should note is if you have a very loose spring, relatively speaking, this very loose spring kind of just wobbled up and down very slowly, but now that we've put in a higher spring constant, this thing oscillates much more rapidly. So that's the effect of having a stiffer spring, is that don't go out and try this, but if you take the spring in a mechanical pencil, let's say, and you squish it and you let it go, it kind of wobbles a little bit, right? And doesn't do it very rapidly. But if you were to push on the hood of a car really quickly, you would feel the car oscillate very quickly and come to a rest. So one thing we see here is that it's oscillating a lot faster. It completes one full oscillation in 2.2 seconds, whereas here we completed one full oscillation after 5.82, no, not 5.82, excuse me, from peak to peak, that's going to be 2 pi, all right, because in this case, our period is going to be 2 pi over the coefficient, so period equals 2 pi over 1, so it's going to be 2 pi units from peak to peak. Here, our argument is square root of 8, and what that means is that, what I'm trying to say here is that if we write period, oh, this is not working very well. Let's try it over here. So yeah, so period for if you have sine of bt like that, then the period is equal to 2 pi over b. And its units are seconds. So that's how many seconds it takes to complete one oscillation. So if b is square root of 8, then this is going to have period equal to 2 pi over the square root of 8 seconds. Now that comes out to approximately 2 pi divided by square root of 8 to about 2.22 seconds. 2.22 seconds. Back up when we had our previous one, our period was 2 pi over 1, which took about 6.14 seconds. So if we take a look at the comparison, and let me call this second function here. I'm going to remove this one. We don't need that anymore. Just so you can see them oscillate, we'll call this function g of x equals, and we'll plot the point 0, comma g of t. So all that's going to do is now watch the red point and the green point. You're going to see the red point move up and down a lot faster. So you see the green point's taking its sweet time. It's taking about 6.2 seconds, 6.3 seconds to complete an oscillation. For the green one, it's taking a lot less time. It's taking about 2.22 seconds. Now what we've used here without really knowing it is this thing called the method of undetermined coefficients, which basically just says that if you have an equation and you know what its template solution looks like. So we made the argument that if you had an equation where it's the second derivative plus ay equals 0, then our guesses were going to be y1 equals sine of something t, sine of bt, and y2 equals cosine of bt. Now we already kind of observed the pattern from our previous example that this was going to be the square root of whatever a is, but let's just go ahead and derive it. Let's just say that we didn't know what b was and we wanted to figure out what b value would make this equation true. So we took its first derivative, we took its second derivative, which would be negative b squared sine of bt. And we can do the same thing for y2 over here. I'm going to go ahead and skip y2 because it's the same thing. Now to find out what value of b would make this equation true, let's say we plugged it in. So we found that the second derivative plus ay has to equal 0. And now I'm not questioning the equality because I'm going to solve for the value of b that makes that equality true. So here we have negative b squared sine of bt plus a times y, well, y is sine of bt, and that has to equal 0. Now, if I factor out a sine of bt, or you just view this as, if you add these together, the coefficients are going to add, right? If you have the same function, like terms, the coefficients add. But you could also look at it as, let me factor out a sine of bt. Now, the only way this is going to equal 0, this product, is if negative b squared plus a equals 0. And so if we want to solve for b, we get b squared equals a. And so b is equal to the square root of a. Now, it's really plus or minus, but we're just going to take the positive value for now. And the reason we're not going to take the negative is because if you take sine of, or I'm sorry, if you take, for example, cosine of a negative angle, so cosine of negative t is the same thing as cosine of positive t, and that's why we're omitting the negative in here as well. And the reason this is true is just because cosine is a symmetric function about the y-axis. So for this angle, it's the exact same value as for that angle that's positive. So that's why we're not taking the negative value as well. Now we will when we're not dealing with sine and cosine, but for sine and cosine, plus or minus the square root of a is not going to make a difference. So we'll just go with the square root of a. So you can see that the value of b that we're going to need here is the square root of a. And that's why up here we saw that the square root of 8 was a function of the fact that this was an 8 here, and if a was 8, then b had to be the square root of that number. So this is just another way to show it. Let's just take a look at one more example. Let's say that we had the mass is 3. We're going to say we have an undamped system. Again, if b is 0, it just means you have no damping force. And we'll just say k equals 17. So our differential equation is the second derivative plus b over m times the first derivative. Well, it's 0 over 3 times anything is going to give us 0. Plus k over m, which is 17 over 3 times y equals 0. Now we know that it's going to be sine of the square root of 17 over 3 and the cosine of 17 over 3, t, but let's just say that we wanted to establish that. So we could formulate, and this is just going to be a good strategy to have when the functions are not always resulting in sine and cosine, but your guess is, I know it's going to be something of the form y1 equals sine of something t, and y2 is going to be the cosine of that same something t. How could we solve for that something? Well, once again, when we take the derivative, the second derivative of y1, we get negative b squared sine of bt. And let's just go ahead and do it in parallel over here for cosine. Its second derivative is going to be negative b squared cosine of bt. Now, to find out what value of b will make this equation true, all we have to do is take negative b squared sine of bt. That's my second derivative. So over here we'll have negative b squared cosine of bt plus 17 thirds of y, which is sine of bt. And same thing here, except plus 17 thirds y, which is cosine of bt. And we know that that has to equal 0. And same thing over here, that has to equal 0. Okay, so when we add these two sine functions together, we're going to be adding their coefficients. We're going to be adding negative b squared plus 17 over 3. So that means that in order for them to add, we want them to add, we want those coefficients to cancel each other out and add up to 0. So if we solve for b here, we'll have b squared equals 17 over 3. And so b, we said we're with sine and cosine, we're not going to take plus or minus, we're just going to take the positive square root because of the symmetry of cosine. Similar kind of concept for sine as well. And then over here, we'll also be able to argue that the sum of the coefficients of the two cosines has to equal 0. So here we'll have negative b squared plus 17 thirds equal to 0. You see that we're solving the same equation. We get b squared equals 17 over 3, and b equals the square root of 17 thirds. So that gives me two solutions, one of them being sine of square root of 17 over 3. So y1 equals sine of the square root of 17 over 3t, and y2 equals cosine of the square root of 17 over 3t. And of course, by superposition, we want to take any multiple of the first function plus any multiple of the second function. And now if we had some initial condition, we could once again go and solve for k1 and k2. We're always going to have, something for the initial position, and we're going to have something for the initial velocity. Sometimes you'll see it written like this. The initial position is written often as y0, initial position, and then the initial velocity you'll often see written as v0. Now, in our next lesson, we're going to look at, well, what if there isn't zero damping? What happens whenever you start to include damping into your model where it's not a 0 in front of the dy dt? Our guesses have to adapt a little bit more because sine and cosine are not going to work exactly. So we'll go ahead and stop there, and in the next lesson we will get into how to solve these homogeneous equations with non-zero damping.